In this part, I'm going to talk about the seismic effects of structure response. I'm going to talk about 3 items: nature of seismic effects, failure modes, socio-economic limit state.
Now let's go to the nature of seismic effects. I'm going to talk about the nature of the seismic effects is an important issue actually whenever you are talking about the response of the structures. Okay, so let's have an example and then I'm going to explain my point or this part of the video. There is a kind of a notion that we need to keep it in our minds whenever we deal with the seismic design of structures. That this is the notion that unlike most of other types of dynamic actions, earthquake effects are not imposed on the structure, but generated by it. Okay, this is an important issue that we need to consider whenever that we think about seismic design. Generated by the structure. So we need to think about this. There is a very unique relation between the seismic excitation and the structure itself. Okay, so based on this notion, we can give this consequence. So if we have two structures founded on the same soil, a few meters apart may have to accommodate vastly different action and deformation demands. Okay, sorry, there is D here. So depending on their own mass, stiffness, strength, and ductility. Okay, understand this? The point here is telling that we may have two structures founded in the same soil, a few meters apart, may have to accommodate vastly different actions. Look here, we have two structures here. They are different, of course, but they are under the same seismic excitation. What will happen here? It is only an example here. This example is an example of two single degree freedom systems. Single degree freedom system means that we have only a concentrated mass at the top and one column, for example, here. It's like similar to the pendulum, okay? One stiffer than the other, one stiffer than the other. Apparently that the shorter one is going to be stiffer than the longer one. This is more flexible, of course. Okay, but the dynamic amplification is such that the less stiff structure, the taller pier here, displaces less than the stiffer structure, which is the shorter pier here. Okay, so even that they have the same earthquake excitation, okay, but the response is complex actually. It is complicated because it is composing of the stiffness, strength, and capacity of each one of them. So this is why the response is really complicated, and we are going to find that even under the same earthquake, the response of the structures are going to be different. Look here, if we apply this Northridge earthquake ground motion on the both piers here, this is real actual piers actually. Okay, so you're going to find that, look here, this is we have the small stiff pier here and the flexible pier here. As you can see, the flexible pier is experiencing very less kind of response. So here, this is a relation between the lateral displacement ratios, which is D at the top. If we go back here, D at the top laterally, and the base deformation or base movement or deformation. So we found that the stiff pier is going to have a kind of larger displacement or deformation composed to the flexible pier. So here we have 2.71 or 2.72, sorry, and here we have 2.05. The maximum here for the for the flexible one is going to be 2, almost 2, and here it is going to be like 2.7. Okay, so now this would reshape our understanding regarding how this happened for these two different structures. Okay, so actually I'm going to talk again about stiffness, strength, and ductility. So stiffness dictates vibration periods, hence amplification. So what is happening here? Why this kind of reduction in the flexible pier? The point is related to the stiffness. The stiffness here, okay, this structure is more flexible than this one. This one is stiffer than this one. And whenever that we have more flexible structure, this means that the period or the natural period, a parameter that we're going to talk about it later, is going to be longer than the natural period of this structure. And this would make the effect on the deformation itself, which is going to make the amplification factor under dynamic loads is going to be higher. Okay, for the case of the stiffer pier, because it has shorter natural period compared to the flexible pier, which is having a longer natural period. Okay, so this is the meaning of stiffness dictates vibration periods, hence amplification. That's the meaning of this word. Change in stiffness causes detuning of the structure, and the input motion hence also affects amplification. Okay, so this is one thing that you need to understand regarding stiffness. Changing the stiffness, as we have done here, this is less stiff than this one. This means that the amplification, dynamic amplification factor here is going to be less. Strengths, if we're going to talk about strengths in the same context, limits describe the region where the structure is able to sustain irreversible damage, hence absorbs and dissipate the seismic action. So here, we're talking here about let's have this. If we have this is the structure here, so having this here, this is the structure, this is the force, lateral force or the base shear, this is the deformation. So what we're talking about here is, at this point or at this stage, stiffness is going to control. After a while, we're going to find that the structure is changing his stiffness. Then we're going to talk about the strengths here. This is why he's talking about about damage, irreversible damage. We are talking about the nonlinear range here. Okay, strength limits therefore lead to the next phase, which is the inelastic ductile response. This is the second stage. So we can say this is first stage, okay, from here to here. Then this is second stage, and then till the end we are talking about the third stage. Here stiffness is controlling, here strength is controlling, here ductility is controlling. Okay, and ductility is related to energy. Okay, always energy or the maximum deformation. Now understand it as for maximum deformation. Okay, strength limits therefore leads to the next phase, which is the inelastic ductile response, which is this part, the middle part here. Ductility is an energy sink, therefore it could be considered as equivalent damping. We're going to talk about damping also, as we explained it before. Okay, so increasing ductility, this means that increasing the energy dissipating of the system. Okay, now let's talk about the failure modes, and I hope that we can, after several slides, we are going to wrap up our section, our video for today. Okay, the failure modes, the idea behind the failure modes for our structure is important, and especially for the seismic design. The main idea that I want to highlight here is that if we are having different input loading, we are expecting different failure modes even for the same structure. How this would happen? So let me explain this. So let's assume that we have the same structure wall here. Okay, it's a structural RC wall, and it is going to be under monotonic loading, as you can see, this monotonic loading is going to be represented by this curve, which is V versus the deformation here. And another case for this structure wall, which is going to be under this cyclic loading, which is going to be applied here. So as you can see F here, and we have the arrow is going to left and right, and we have deformation to the left and right. So here it is severe cyclic loading for the same wall, and in the previous one it is monotonic loading. Okay, what do we want to understand from this example? Actually, what we want to understand is that if the loading is different, the failure mode is going to be different. Whenever that we are going to apply the monotonic loading, we are going to find that the structure is going to fail under flexure. Can you imagine this? Let me use the pen here, sorry. So let's, here, whenever that we apply the load at different level, let me use the red color. So we are going to find that here the load is going to increase, and actually the structure is going to, yes, to move based on the increase of the loading. Stage 1, 2, 3, 4, 5, then this is 2, 3, 4, 5, and so on. What is happening here? It is exactly cracks here. The cracks are larger at the bottom and going smaller at the top, and we're going to find that the entire structure wall is going to maybe deform or collapse under bending moment, under flexure. So the failure mode here is flexural failure mode. This is under the monotonic loading. If we go to the severe case of cyclic loading means that the load is going back and forth as we indicated here. Under heavy cyclic loading, you're going to find that the structure is going like this one time, and then it would go like this another time. Okay, this means what? Actually, the cracks are not going to propagate along the height, but there is another type of failure mode would be triggered, which is shear failure mode. This is what we call it, the shear failure mode. Okay, so we have different type of failure mode based on the different type of the loading or the applied loading. This is very important, and this has a paramount importance in seismic design in general, that we need to understand the seismic input or the seismic loading. What is the type of the seismic loading itself? Whether it is a monotonic, as we are using in our structure or pushover analysis, for example, or it is like severe cyclic loading, which is very similar to the earthquake. Actually, the earthquake is very similar to this severe cyclic loading, going back and forth severely. But this one is not right, or I do not want to say not right, but actually it is an approximation, but maybe it is not representing well what the earthquake is going to do for the building. Okay? Anyway, what we want to conclude from these two slides for our failure modes is, if the input is different, if the input loading is different, this means that our seismic response of the structure is going to be different, and the failure mode is going to be different. This is what we want to highlight in our in this part of the video. Okay, now let's go to the last part, and after that I'm going to wrap up this video. I'm going to talk about the social economic limit states, and they are actually important for our understanding whenever we are going to design our structures. And as we are going to see in the performance-based seismic design, we need to understand what is the meaning of social economic limit states. Okay, so let's go to some important definitions. I'm sure that this video actually is it is full of definitions and a little bit like long definitions and sentences, and there is no much figures and not so many fancy figures, but I am sure that this video is very important for the making the right foundation for seismic design. If you could understand the items and the definitions that I have explained here, you're going to find that smoothly. You're going to understand the process and the procedures involved, or the procedures that is needed to be understood for the seismic design. So actually there are like three main different levels of earthquakes. We need to categorize our limit states based on them. Okay, so we have like different limit states, and they are categorized based on the level of the earthquake. What is the meaning of this? I want to start from this slide first, and then I'm going back to the previous slide. So we found that if we have the earthquake to whenever that we are dealing with small earthquake, the response of the society to the small earthquake is different than the response of the society whenever that we have higher or medium-sized earthquake, which is having range of 5.5 to 6.5 Richter or magnitude scale, on a magnitude scale, and the response of the society for a large earthquake like from 6.5 to 7.5, it is different than the small size or the medium size. So we found that under small earthquake, okay, we need to, from the engineering limit state, from the engineering point of view, we are not expecting our structure to have significant damage. We are expecting our structure to have insignificant damage. So this is the engineering limit state that we are going to link with this level of earthquake. And we found that from the socio-economic limit state for the society, we want our facility or our structure to continued operation, means that the operation is not going to be interrupted or not going to be stopped. So if we have a facility like a hospital or a school or something similar, we do not want the operation of these facilities to be interrupted because of small earthquake. Okay. The second level, which is the mid-size level, we found that the limit state or the engineering limit state that we want to link with this medium size is the repairable damage. Repairable damage. This means that there are some damage in the non-structure elements of the structure or the facility, but we can repair them. So the socio-economic limit state, which is associated with this engineering limit state, is limited economic loss. We do not want, we can tolerate, in this case, we can tolerate the interruption of the operation of the facility, but we're not expecting to have a vast or great economic loss. We want to limit our economic loss. Okay, so this is the philosophy in this level, or at this level. The third level, which is going to be for large earthquakes, we are going to put an engineering limit state which is collapse prevention. And the socio-economic limit state is that we are going to tolerate the operation, we're going to interrupt the operation. We are expecting vast economic loss, but we want to maintain life, which we call it life loss prevention. We are not allowing we are not tolerating life safety. Okay, we are not tolerating the life or loss of life in general. So these are the main three, we can say, levels related with the engineering limit states, and we can relate them and link them with the socio-economic limit states. And if you look again from the structural characteristics, whenever we are talking about small earthquake, we need to think about stiffness. Do you remember the serviceability? If we're talking about medium size and we're talking about repairable damage, okay, then we're talking about strength. And if we're talking about large earthquake, we are talking about, or we should think about, ductility, okay, the maximum deformation for the structure, which is the collapse prevention limit state from the engineering limit standpoint. And then we are going to link it with the life loss prevention. Okay, this is not exhaustive kind of levels. We can find other people, other researchers, they use maybe different level, maybe 5 or maybe more limit states with different levels of earthquakes. So, but this is one of the robust and one of the most commonly used and highly accepted and widely accepted categorization of limit states, links with the socio-economic limit state and the engineering limit states, with the level of earthquakes and the structure characteristics as well. Okay, so now let's go back to the previous slide. I'm going to read it and you're going to understand, I think, what I have explained before. Under small earthquakes, a society seeks the least disruption from damage. This may be considered as an uninterrupted use limit state and is clearly most correlated with structural or structures having adequate stiffness. Again, so we are linking it with the structure and the stiffness of the structure to resist undergoing large deformations. Under medium-sized earthquakes, a society would tolerate disruption of its endeavors, but would seek to minimize repair costs. That's the point here. Repair cost is important for medium-sized earthquakes. This may be viewed as controlled economic loss limit state and is most related to the structure having adequate strength so that the damage is limited. Under large earthquakes, a society would accept interruption, high economic loss, but would seek to minimize life or loss of life. This is a life safety limit state and is most affected by the ductility of the structure that enables it to deform well into the inelastic range without significant loss of resistance to gravity actions. And this is the main, the gravity actions. It is highly linked with the life safety because we want to maintain the system to sustain its gravity actions. Okay, so actually this wraps up our video for today. We have explained different items, different topics. I'm going to recap what I have explained up till now. I'm going to this main contents, just recapping what I have explained. I have given some definitions for strength, stiffness, and ductility, and after that I explained about the strength versus ductility based response, and I mentioned about the meaning of or the difference between direct design and capacity design, and what is the relation or what is the advantage of the capacity design over strength design. And also I elaborated on the difference between the strength, the direct design for strength design based on force design or ductility based design. And for the third point, I was talking about member versus system level considerations. So I have explained that we need to take into consideration the force deformation relation at the member level and component level, and then at the system level. And then I talked here about the nature of seismic effects and I mentioned about different issues related to the nature of the seismic effects itself, if the system are going, or the systems are going to be different, and their structural characteristics under the same natural seismic excitation, they are going to respond differently. And then I talked about failure modes. Based on the seismic demand or the type of imposed load, we are going to find different failure modes, and we mentioned about flexural failure mode, and another one, shear failure mode. And then I talked about the most commonly used socio-economic limit states that you're going to see in seismic design in general. This ends and wraps up my video for today. I hope that you have understood it, and I hope that you can understand the different items that I have highlighted today regarding these topics of this video. Okay, thank you, and see you in the next video.